last time talking about fatigue when you don't necessarily have a crack in the material to begin with. It's probably more used in terms of volume of material as a life assessment approach than what we talked about with the stress intensity, the fracture toughness, and all those concepts. One of the reasons is it's a little bit forgiving, so you have a lower safety factor. You can build lighter components if in your design you don't assume they already pre-cracked. So the counter side is you have to make sure as part of your finishing process that you minimize the extent of notches on the surface or little micro cracks from the fabrication process. So more specifically, we'll talk about fatigue limit. There was a question at the end of last class, so we'll cover that in more details and tie crack initiation with crack propagation in the context of fatigue. Then we'll talk about what happens when the load is not always the same, because I think I wrote on the board for you guys a couple times this sinusoidal loading, but in real life, a lot of times you have variable amplitude, so it's going to be a little bit of vibration, and then you have a big burst in load at some point. So we'll talk about how we take that into account for design. We also talk more about what happens if the varying load goes through zero all the time, or if it's always positive, for example, because that's also affecting the life. And a lot of times we don't go back to the lab to run tests in the exact same condition. We use rules to combine different mean stress level and evaluate how they're going to rate. So we'll go through that in details. And I want to tie it back into what happens with the plastics. Now with the plastics, it's more of a creep effect. But I think you realize, like even the last lecture when we were talking about the Paris equation and how the crack grows, and then I talked about, oh, you can have stress corrosion cracking, and now it's growing as a function of time as opposed to number of cycles. So the general concepts a lot of times are the same. It's just the details and how you end up using it that are different. So it's the same for the plastics. It's creep, but we use a very similar approach to determine whether our design is sufficient, whether we need a greater wall thickness, whether we need to derate the pipes and say, oh, if you're going to use it with varying pressure inside the pipe, now instead of being allowed up until 200 psi, it's only going to be up to 100. Those type of conditions are part of some ASTM requirements a lot of times, that if your conditions are more severe than just a constant pressure, then you have to derate the strength of the plastic. So the fatigue limit, and that was a little discussion. We didn't have any graph to tie it back to, so I put a graph here. It's an SN curve, and as you decrease the load here on the vertical axis, you get more life before you break, and then you have a solid line that goes to a flat. That's for many steels have this behavior where they will go for an infinite number of loading cycles without breaking if you are below a certain stress. And what we were talking about yesterday is the case of the dotted line, which would be any copper alloy, aluminum alloys. There are many that will fall in this category here, where you keep having to decrease your load level if you want to go to a greater life. You may want to be aware, like for welds, for example, some weld geometry will show this plateau here, and then eventually when you get to 10 to the 9 cycle, it's going to start going down again. And it's just a different process of initiating the crack that happens in this situation. So it's what it is with materials. Very rarely we have absolute. So if we're talking right now about a plain piece of steel, it will have that asymptote. If we talk about an assembly, it's possible for a large number of cycles that we have another mode of failure starting to take place. So endurance is normally considered at 10 to the exponent 8 cycles, and the fatigue limit is 10 exponent 7. It is, I guess it's more important to remember the fatigue limit because it does vary depending on which exponent you use. So some people may use 10 to the 6, and they'll have to say, my fatigue limit at 10 to the 6 cycles, or 10 to the 8, but the most common is 10 to the 7 when it's not clearly specified. The other aspect of the stress strain curve, and we're going to tie back here to, remember I showed you the fracture surface of some plastics where it started in the center and then it popped. And I said that it didn't take a whole lot of time to start many cracks around a very small particle in there. And what happened for that example is we were relatively high in stress. So say we were right about here on the vertical where it says crack, and therefore from the beginning we had a little bit of propagation. They were very small cracks, but then they were growing like fingers and merging together, becoming a big crack, and eventually it fractured. Well, as you lower the load, what happens is it will take more time to start a crack. It happens in different ways. We'll say that essentially the nucleation portion of it will become more difficult because now you don't have as much of a driving force. If it's a little bit, if you cool a fluid super fast, you have a big driving force for forming crystals, so you'll form many of them. Well, in our case, it's the opposite. So at low load, it's very hard to form these defects in the material, so it will take a lot of time to actually form them. Now, what happens when you have a real component? And I picked here, it's very small. These components are only about this high. They have turbine vanes for the compressor part of a turbine engine. So it's not really hot. So it's hot a little bit, but it's not creep dominated. When you get behind the combustion, you have all sorts of other issues to deal with. You have fatigue, you have creep. But for this example here, we're going to think of it as relatively low temperature application. And so we have all these blades that are mounted on the rotor, so they held at the bottom. And as the air pressure, you have on the left-hand side the leading edge. So the whole blade bends back when it's in service. And we see at the very corner here, that's the defined element solution looking at stresses where you have this radius transition between the base and that leading edge. That's where the stress is the highest. So what happens, so we'd already decided it was going to be low temperature, and then we look at the stress level there. It's a smooth surface. All right, so we think of it a little bit like a tensile specimen. And we use an SN curve type approach to see what stress level we're going to look at. Now, here's where the fun starts. So we have a stress level, and then we have the number of cycle. I will just draw a straight line here, because we'll put a log. That's going to help. And a little log here, why not? Okay, so we're designing this blade we know each time they turn on the engine, the RPM ramps up, the temperature goes up, and you have this centrifugal force that's building in, and then all the wind effect. It's all happening. So we'll call those like the super cycles. So we'll put them here high in stress level. And then when you're up in the air or at any point in time, just because of the rotation, there is vibration. There's always going to be some vibration. The issue with vibration is you're looking at a very high number of loading cycles. So we'll put it somewhere here, close to the bottom of the curve. So for a general application, the question is, how do we deal with it? You have to be able to resist this load that's higher and a lower load as well. That's the vibration load. And that's where there's essentially one main empirical relationship that will tell you that the damage, the total damage, would be the fractional sum of what you get at the highest stress level and what you get at the lowest stress level. It's used in various ways. So if instead of this very simple example, we had a whole spectrum with loads at all the increments in between, we'll just use a very more complex variation of this method. So all it says for Miller's rule, we're going to write it in a general form. So summation of damage, I'll say, is essentially the number of cycles you have at a given load over what it takes to fail at that load. Now you can use it sometime on a logarithmic scale, so that it gets a little bit more tricky to decide exactly how you're going to use this, but it gives you a general idea that we're not always going to be loading at one load and figuring out what happens there. And then there's another way to think of it is because of those high loads, it's possible that I'll start cracks that I would never start under these conditions. So even if, say, I end up completing the curve like this, if my curve ends like this, because I start a crack on those high loads, now it's quite possible that the crack's going to continue to grow at the lower loads. So I'm not going to say to look only for the big cycles, but the big cycles essentially sometimes end up having a bigger role than Miller rules will say. And that's why it's like any other tool. You can use it, but it may not be conservative for the high loads here. And that's really something to think about when you're looking at a specific application. A lot of times people will run full-scale tests as well. And then the advantage of doing the full-scale test is you can take into account some of those I would say rather complicated issues that are hard to calculate otherwise. Another method that's used a lot is the rain flow method. That essentially takes a random spectrum of load, and by projecting it in the horizontal direction, it looks for different amplitudes, and you can essentially build a table that will tell you, okay, so this is my delta sigma. We start with 1, 2. It will make a histogram for you, and this is how many cycles I have for it. So we'll call it small ni. So you really end up with a very long, this could be hundreds of line list of different loading conditions with the number of times they show up in your overall spectrum. And once you have that, then you go to your material property chart to find the big N sub I for that condition, and arrive to some estimate of your fatigue life. Now, we haven't talked about safety factor, and we'll get there very quickly. It may even be the next slide. But
on Myers' rule, though, the failure is when it equals 1, right? So when C
yeah,
is equal to 1, that's
yeah,
for failure.
yeah, but it's you can't take it too seriously. So it could fail at 0.8 or 1.2. It's an indicator. That's why I didn't want to get too specific about it. But it's a good question. So we talked about all this at this point. Variation. It's actually probably the most important thing to remember, that out of an SN curve, you get a lot of scatter, and you can have different results if you prepare your specimen differently, if they're machined slightly differently. For example, if we test plates, and we talked about residual stresses and all those concepts. So if you test plates and you machine them down because you don't want to have the full thickness, you'll have a different curve than if you do the full thickness. And that's one reason why some of the specifications, STM specification for sheets in steel, for example, will require full thickness specimens unless said otherwise. So you can use them unless if it's involving a stamp component, a bit like Professor Eager talked about. You essentially form it, but you still have this whole thickness with residual stresses on both sides. You have different properties in the middle. You have different properties in different directions, but that's your product. So if you want to know how resistant it's going to be in cyclic loading, you essentially have to test something very close to it, as opposed to a nice specimen that's machined out of a big block. That wouldn't work. It doesn't matter if it's the same chemistry. There are too many differences in the process. Okay, so what we're looking at here on the plot is just one set of data, and these were blades, cast components, all done the very same way as far as the different colors. So the blue were all done the same way, the red were all done the same way, and you see variation. For those who were a little bit late, we don't have handouts because the admin wasn't here today, but it's posted on the website. So we have the blue and the red. The point I want to make is there is scatter. If you take all the lines out, I'm not going to say it looks like a cloud of data, but it's not that far from a cloud of data. Now we are on a logarithmic scale, so if we were to take away the logarithmic scale, it will look more like a straight line. So we have our fatigue limit here at exponent 7, and I'm just showing you these confidence interval. I believe those were 95%. So there are at least, there's a handful of ASTMs that speak specifically to how to do stress life, fatigue testing, and analysis. So there's one that will tell you exactly how to draw those confidence intervals. But the point I want to make to you is you don't feel as secure because of the variation over here. We had about 10 samples about what it would be if we tested 100 samples. How many would really fall outside those lines? And that's why the confidence interval lines are spread out. And instead of, as engineers, you see the average curve and you say, well, I like to use that right here. So I have an endurance limit of 25 KSI. But in reality, because you want a reliable design, you have to take into account that maybe it's not 25, maybe it's significantly less. In this case, we get around 17 with the confidence interval. There are multiple ways to do the regression. When we have the data, you can minimize the error this way, so in terms of the number of loading cycles, or you can minimize it in terms of the load variation from one case to the other. And depending on your application, there's one method that would be more conservative than the other. Sometime what I did is I did both, just mostly to see the difference. It takes a little bit more time, but most of the time, the hardest part is to get good data. Once you have good data, putting up the confidence interval plot is not a big deal. Now, this was a comparative analysis in the process of reversing essentially a component that was built, certified, and used, and then a third-party vendor wanted to make one that was as good. So he had to prove that with respect to all characteristics of the component that he was able to make it as good. So that was toughness, fatigue, strength, dimensions. It is a very long list of things to verify. And you guys may have seen this before, but I thought I'll just bring it up because it's something you can use on a lot of projects where, say you have your MIT bottle right here. If for any reason you wanted to do any modeling of it, the easiest way is to send it to a lab. They have this laser scanner head here mounted on a tripod, and it's all with the computer screen, and they'll literally just go around it. About 10-15 minutes, you'll have the whole surface scanned in at precision at less than a mil. I mean, what I normally ask for, I say, I'd like to have a coarser resolution because I don't want to deal with all the huge files if I don't need to. But it gets very precise, and it's essentially the combination of the laser with the positioning 7-axis system that's very easy to handle. Somebody can do it, they do it by themselves. It's just a one-man operation. They do it on a large scale for buildings as well. It's just out there. So if you need to know exactly, and some of the large-scale ones, it takes longer, so they'll put the machine there and it's going to scan overnight the whole room. They have to put it at different locations with reference markers. It's not super sophisticated in terms of the physics and the science behind it, but it gets helpful. One thing that we've done once is we used the scan of a blade, and then we did a stress analysis with finite elements just straight from it, without even drawing it. So I actually showed you that. That's what I was showing you was coming from a laser scan data. So it's helpful to know sometime if you're on a project, all those different possibilities that you could be tapping into for a given, and there are a lot of them. This is a case here that I want to introduce to you to talk about the effect of mean stress. The general idea is with bolts, if you want a bolted connection to be resistant to fatigue, do you think you want to torque the bolts a lot or not a whole lot? That's a question. So not a whole lot.
Which direction is it getting loaded? Axially? Is it an axial direction?
Yeah, we're not talking about a shear loading of the bolt. That's right.
Not a lot.
You don't want to load it, right? Okay. Well, Well, so I think we have to draw it so you understand better. I don't want you to take my word for anything. So, so we have a bolt hole, and then we have two flanges. And then we'll put the bolt right here, going across with the nut and everything. And I sort of make it thin on purpose. When we say preload, so when we torque the bolt, we'll generate a clamping force. I think everybody could agree with that. And I'll just put a number here. So I'll put 10,000 pounds for this one. We'll call it preload. So what happens, I should make this. So now we have more of a real geometry. What happens when you start loading this connection, as long as you still have those contacts here, if you don't have a separation right here between the two flanges, it's a block. It's essentially all connected. So it acts as a big spring. But so let's put it this way, it's super stiff. If we do it in a way that we'll start getting a separation between the flanges, like we have here. So now I have the bolt. So over here, the 10,000 pound preload end up really being carried just where the bolt is. Nothing else is touching. So that may be a way to think about it and remember it for a long time is, in this situation, this is how much volume of material I have to transfer the load from one side to the other. Given that, this is much stiffer. This is a supersized spring. So I'll already draw it as, this is my spring right here for this situation. And then here we have a super small spring. So different size springs mean, for the overall connection, means you have more variation in stress level in this case because you get more displacement. If you're going to move this bolt by a whole lot more, you get more strain in it than if it's still tight in that connection. So what happens here, it's good to put it this way. What happens here is, yes, you have a lot of load to begin with because you preloaded it, but that load will vary by about 7 times less than if you are just hanging. So with the preload of 10,000, if now we add, so we'll call it our service load of 10,000. So in this case, we'll have maybe, it will go up to 1,500 or something like that. No, it can't, yeah, hold on. No, you can't exceed it, I'm sorry. The only way this works is if your service load is less than your preload. So I'm sorry for the confusion here. But at the same time, I think it's kind of part of the process. So if your service load is less, you stay connected, and your load here would only go up by, I'll put it at 7, why not, right? So go up by 1,000 in the bolt. In this case here, because it's really free hanging, now you get the summation of the two. It really becomes more of a direct load. So it's a great benefit, because when you think of bolts, they have all these threads and everything, and they're small in general as opposed to the component that you use them for. And therefore, the fact that by loading them, you can reduce the stress variation. I mean, all we're talking about here is the variation. Because in both cases, yeah, you generate a lot of tension in the bolt. There's no doubt about it. But in this case, it's shielded, so you have less variation. And the other case, you just have more variation. Yes?
Will you not have a lot of problem with creep?
Creep of bolts. I haven't really seen it a lot. I've seen it on some cooling towers. And what were we doing then? Yeah, we were not designing for cyclic loads. So yes, it becomes a different situation. My general comment is, if you're going to have creep, you'll lose the preload anyway. So it's not going to matter too much how much you've put on to begin with, sometime anyway. So this is really for a situation that you want to prevent the slip and the movement between the two flanges that are facing each other. And by the time if you are able to do it, then you're reducing your amplitude of cyclic load. And that's what is done for a lot of bolted connections. Now, the way to do it, so you have to evaluate. So I'm talking about the bearing right in the middle between the lower portion and the upper portion here. And the good thing about one of the idea I've put out that image is there's a range of loading here too. So if you have if you're retracted and right over the crane, you're not going to have as much fatigue as when you're fully extended and overreaching. And then when you're overreaching, it's when you decide to go all around. That's the highest load you'll get, because you really move from a tension to a compression situation on the connection. So we're looking here at that bearing through fine elements. Doesn't mean you need fine elements to design a system like this, but in this case it was too compliant that we couldn't use just a simple engineering method. So we're really looking at how many pounds each of these bolts carries through the loading cycle. And by the time we know that, it varies. So we'll have, let's do it here. So we're looking at one bolt, for the bolt that's the most highly loaded for some reason. So say it sees a combination of mean stress. So we have a mean value, and then we also have an amplitude. And if we're going back to our plots, so the amplitude, normally we'll cut it by half here. So it'll be the range divided by 2. So this would be twice the amplitude here for this value. And then the mean value is just right here. So what I need to introduce to you through this example is the Goodman diagram, which essentially talks about those two values. So we have the amplitude and we have the mean stress. It gets a little bit more complex because there's no number of cycles anymore, and there's no stress level. But we talked about our bolts. So if we take a bolt that is not preloaded, and it goes through a series of cycles of tension and compression, then it means our mean value is here at 0, and we get a certain life that's actually pretty good. If we put a tension in the bolt that's, say, the yield strength, well, that's not too good, right? We're going to start changing the dimensions of it. So as far as fatigue, normally we'll say we don't want to get there. We don't want our mean stress to reach the yield value. And if we keep going, we may reach here the ultimate tensile strength as our mean stress. Forget about, right now I'm putting no amplitude because we were right on the axis. So I'll put it right here. So that's to fail just all at once. So I think so far we covered this as being our unloaded bolt that goes through tension and compression. Then we have this, which is yielding of the bolt in tension, and then breaking of the bolt in tension. So all we do is a straight line. That's Goodman diagram. It doesn't require a whole lot of testing, and it allows you to take into account the variation in mean stress. That's probably all you need to know about how to deal with mean stress. Now, I will tell you, and you can even see on my plot there, that I have some curves that have a curvature, because people will arrive with more complex ways of going from here to here. There are 3 or 4 models, and then there is the question, when I drew this point, it was for a certain number of cycles. And we haven't talked about that, but essentially this would be, say it's 10 to the 7 cycles. If I decide I want to do 10 to the 5 cycle, then I'm allowed to a greater amplitude, so I have another curve that will go above it. And that's what my plot shows. On my plot, when you go from one curve going up, going up, going up, each time it's for a fewer number of loading cycles. It still end up essentially at the same point where the ultimate tensile strength is 150, which is essentially the same thing that we'll project right here. The reason I stopped it here is I really don't see the point of starting to yield, because now you're losing your preload. So a lot of times what we'll find is exactly like this, where if you design the way some of you wanted to do it, you could be in this condition right here. But we talked about reducing the amplitude by a factor of 7 by adding the preload. So say we end up right here. That's in the safe region. That's below this 10 to the 7 line that's going across, whereas here we were going to fail by fatigue. So that's how we use the preload in practice, to be able to use smaller races with fewer bolts. Everybody, it's always easy to say, oh, I'll just put bigger bolts or more bolts, but you always have space constraints, you have weight constraints, so you really want to go for what you need. What you need is a lot less if you preload the bolts. And rule of thumb is around 70 to 80% of yield is where you get the biggest benefit of preloading. If you go higher, it depends what the material is. I had a project where they were building a structure to host a nuclear waste facility, and the guys there just really over-torqued all the bolts. They were asked to do up to so much torque, and they did a whole lot more. And we were trying to figure out if it had an impact, and really we couldn't find any problem with it. But these were structural bolts. These were not super high strain bolts or anything. So just specific for that application, we found that kind of over-torquing, if you don't break it, and also if you don't essentially cut the threads. If it gets loose, then that's, it's still in place, but it's useless. So they had to go back and check for loose bolts. They found a few, replaced them. That's kind of, when we talk about fail-safe, it's better if the guy is turning the bolt and everything falls off than it just gets loose because you broke the threads. So that's why the way the hardness of the nut thread and the bolt thread is made is to try to avoid getting a failure of the nut. It's preferable to have a failure of the bolt. So that's a side note, but I think for your benefit, the idea is don't worry if you have data for just a normal test that we will do tension compression. So the data that we're looking at there to feed this whole diagram is essentially like this. So you use this to make that data point at 10 to the 7th cycle. So you need a fatigue limit for this standard situation, and then you can go and look at a range of preload. You can use that, I showed the bolt example, but you can use it for any application. I think you know that. Plastics. The main difference with plastic is just under load at ambient temperature, they'll keep deforming. And that's what this plot shows here. So if we take 20 degrees, it's on a log-log scale, and it's going to go linear, and then eventually it turns to another regime of deformation. So you get a change in slope at high life here. It gets to be a challenge because I could go to the lab, run a test for a month, and then try to extrapolate to 50 years. And I can only do it if I know if I have a transition or where the transition is going to be in behavior. You can see from this plot that it's a very steady, the transition point with respect to temperature is very steady. So what it tells us is, oh, I can run my test at higher temperature because it doesn't take as much time. I'll go through that transition over here. It may take me 1,000 hours. 1,000 hours, I get the whole red curve at 80 degrees. Now I have to decide how much effort I'm going to spend in getting more of the other curves to be able to reconstruct the whole history. But the idea is, at the end of the day, it's for a long time use. So you have to have enough combined data, either by varying the stress level, by varying the, in this case, the temperature, the testing temperature. You have to develop enough knowledge about your material to get the curves, and that's where you see the dotted line here, These were not tests that were actually run. These are extrapolation of what is known based on the combination of material properties. For at the end of the day, if you need your stiffness for the service life that you're looking at. So if you know that your stiffness will reduce by a factor of 4, and your strength's going to go down by maybe a factor of 2 or 3, that's essentially how lower you have to design for in the long term. So it's very sophisticated in one sense in terms of trying to predict the future, but when it gets to using the data, once I have a modulus for a long time from now, it tends to be kind of a straightforward, well, good enough approach to compare materials also, because this is all another situation where the history of using of a material will tell you, well, I really want to have so much safety factor on my 50-year modulus or whatever it is. Now, in some applications, and I worked, for example, on gasoline storage tanks that are not pressurized, and what happens there is the load is not the same. So you have bending of the tank over time. So say the tank starts round. These are under the parking lots at the gas station. And then if I keep essentially putting all the dirt load on it, eventually it becomes a little bit more elliptical. So I have tension here and compression on the other side. It's a bending situation. Same here, same there. And it's simplistic to think of just one modulus for a whole tank, because the stress level can be 0 right in the middle here. It's going to be maximum tension on one side, maximum compression on the other. So one way that it's done is to assume that it will still be a linear viscoelasticity, which essentially means that I'll get a gradient in reduction in modulus that's proportional to the difference in stress level, which is not true, but it's an approximation that a lot of time we're faced with doing. The reason I say it's not true is because if I put 5 KSI in creep on a plastic, and then I decide to put 10, well, at 10 KSI, it's going to deform a whole lot more than twice faster than at 5. It's just the way material flows. And it's not something that's taken into account by a lot of the equations. You have to run more sophisticated analysis, which is done sometime, but not always. So that's the tank. Any question for today? It should cover pretty much all I wanted to say about stress life, where you just figure out how many cycles you're going to have or how long it's going to hold. You look at your material property. If you have variable amplitude, we have Miller's rule. If you have mean stress, you have Goodman, and I mentioned there are others. And for plastics, a lot of times you end up using a simplified approach to determine what's going to happen on the long term. Time is very important. Well, thank you for your time.